In this question, I want to talk about scoping. I want to talk about what happens when I refer to variables in a Python function. Is Python passed by value, passed by reference? Is it something else entirely? And what on earth does that non-local and that global keyword actually do? Let's take a look. One of the things that we need to consider is, what's the scope of a change? When we talk about scoping, this is what we're really talking about. We're talking about identifying how far we can change something, or in what context something can be changed, in what context something can be seen. Let me take a very helpful little context manager here and run you through a couple of simple, small examples. Here I have a function called f. In this function, I take a local variable x, and I increment that local variable. Outside of this function, I have a global variable x, and I call this function. And a question would be, well, what happens in the interaction on the outside and in the inside? On the outside, before, the value of x is 1. On the outside, afterwards, the value of x is 1. So you can see this function is incapable of reaching out and changing that value at that global scope. And inside this function, we can see that this plus equals 1 actually had an effect. You can see the value goes from 1 to 2. And this is largely how we'd expect something like this to work. If we wanted to capture the result of this, we'd probably have an explicit return, and we'd take a look at, we'd explicitly return this value x, and then we'd assign it on the outside. Take a look at another example. Here, we do not pass in x as a local variable. Instead, we try to rely on x still being available as a global variable, and we see if we can increment this. But we get an error here. We get an unbound local error. And it may not be clear to us why there is an unbound local error. Why is it that Python can see this value, but it can't seem to change this value? What's limiting the scope of this function, or what's limiting this code from being able to affect the global scope? Well, one of the ways that we might solve this is we might note x as being a global variable with this global keyword, and then we can see that this behaves the way that we expect. On the inside and on the outside before, the value of x is 1, and then afterwards the value of x is 2. And so it appears that we are able to, from within this function, affect something outside of our local scope, affect something in the global scope, and all it took was this global keyword. What exactly this global keyword is doing may still perplex us. Let's take a look at another example. In this example, we have x at the global scope. We pass it into f. We update it in f. We do a +1 operation, and then we return it. And this is more or less what we might do if we wanted to have some function operate on some value like an integer, update it internally, and then return it, and then capture this result on the outside. And here we can see very similar behavior to what we had before, except we are using the local scope in this case. We're not reaching outside of our scope in order to change something. This example seems to make quite a bit of sense. Now, let's do another example that's only very slightly different than what we had before. Here, we have x, and it's not an integer anymore. It's a list. We pass it into the function, and we do a .append operation. And we see something kind of interesting. This function was able to affect this variable x in the global scope. You can see in the afterwards, we see an effect. It didn't revert back to the empty list. And this may cause us to ask questions like, is Python passed by value? Is Python passed by reference? What is the calling convention? When we pass data between these various scopes, what are we passing around? And why is it that in the case of x being something like an integer, the operation to change this seemed not to have any effect in the global scope, but when x is a list, the operation appears to have some effect in the global scope? And now we're getting a little bit confused and a little bit perplexed. Let's take a look at our next example. Here, in this next example, x is a global variable, and you can see we don't pass it in, but we can affect it from the internal scope here. And we didn't need a global keyword. In fact, it appears that if we add a global keyword here, nothing really changes. It seems completely optional. It may not be clear to us why it is that that global keyword is optional. It has no effect whatsoever. It doesn't make this code more or less correct. It doesn't really add or change anything meaningful for this code. Let's take a look at another example. In this example, what we're going to do is we're going to have a list on the outside, and we're going to append 1 to it, and then we're going to return it. And here, this is actually just for completion purposes. You know, here this does more or less what the previous one did. We can, of course, return the value of this x, but the question might be, is this making a copy? Is this changing the underlying data, what's actually going on here. But that's pretty straightforward. Let's take a look at a case where we have a function that's defined within a function. Here, we have a function g that is dynamically created within f, and it's doing this plus equals 1 operation inside this function g, so I suspect that means that it's affecting this x here. That's neither in the local scope nor in the global scope, but is somewhere in between. And let's see what happens when we actually run this code. And when we run this code, we get something a little bit bizarre. We see another unbound local error, and there's something erroneous here. And the solution to this appears to be the case where we have to add a non-local keyword in order to make this work. But just like that global keyword, yeah, I can add it all over the place to just kind of force it to work. But what's really going on that's causing this to require this non-local keyword? Now, one thing to note is the scope of this change is still limited to this scope here. You can see it's not changing anything at the global scope. Now, let's take a look at another example. And we'll do the same thing, but we'll do it with a list. And note, 1, we didn't need a non-local keyword, and 2, the effect of the change is visible in the global scope. And so when we look at this, we're scratching our head trying to figure out, okay, how does scoping in Python actually work? Why did it seem to work with the non-local keyword in some cases? In other cases, I didn't have to add it. What's actually going on here? Well, the explanation ends up being fairly straightforward, and it requires that we look at the Python bytecode. Here is the Python bytecode for a function that refers to a value x that is not defined locally. That's clearly a global variable. Now, this value x does not have to exist prior to the definition of this function. And in fact, it's pretty reasonable that if this were referring to, say, a function g, we might define g after we define f. We don't need to necessarily have this defined ahead of time. And you could think there are circumstances where even then it might be difficult for us to find a strict linear ordering for these. But we have x that hopefully comes into existence at some point after the definition of f, or came into existence at some point before. And when we look at the bytecode, we can see there is a load global keyword here. If we make this example slightly different and we have x passed in as a local variable, we can see that the bytecode changes very slightly. Instead of a load global keyword, we have a load fast keyword. And if we again change this example very slightly and have x passed in at the top level and then refer to in a function that is dynamically created, we can see this code changes ever so slightly. It now becomes a load deref. Here's the story. Python can statically identify where a name binding comes from. When we think about variables in Python, we shouldn't think like we do in C or C++ about memory addresses. We should think about names. We should think effectively about every part of Python code has some sort of correlation between some names and some objects. This is what the local scope looks like. And if we do locals, we'll see this represented as a dictionary. Now, I say very carefully this is represented as a dictionary because it may not be stored or managed as a dictionary, but you get the general idea. So we have these name bindings. On the left-hand side, there's the variable name that we use. On the right-hand side, there is the actual underlying object that it's referring to. And clearly, multiple names can refer to the same object, and the same object can have multiple names. Well, Python knows how these bindings come into existence, and it can see those statically. It can see you did an import x, therefore there is a module named x that's available to you. It can see you did a from something import x, therefore there is something from this module called x that's available to you. It can see you did x equals for x and whatever, x assignment expression equals something with something as x, except something as x, although this one has a little trick at the very end, it does a del x. But it can also see class x, def x, it can see any one of these, and it can see those from the source text. When Python needs to figure out how to load data in order to perform some operation, when you're adding x and y and it needs to figure out how to load x and y, well, the Python parser wants to pick the fastest possible way to load these. It doesn't want to search through all the possible places where it can be. So the Python parser makes use of these static forms to statically identify, that is to identify prior to the function being run, when the underlying bytecode is generated, to identify, is this a local variable? And if it's not a local variable, well, are we in a function that's defined within a function, therefore it's a closure variable? And if not, I have no idea where this came from. Maybe it doesn't exist yet. It must be a global variable. In general, the Python parser looks for these static forms, and if they're in the local scope, it's a local variable. If they're in a scope one higher, a function defining a function, that's a closure variable. And if it's neither in those places, then it's a global variable. There's actually one more option, load name, where it does do the searching, although that's relatively difficult to produce in the bytecode these days. It used to be a lot easier to produce that with things like import star. Well, load fast means I've identified this as a local variable. Load deref means I've identified this as a closure variable. Load global means I've identified this as a global variable, and that's how I'm going to load it. That's the location I'm going to look in to find this variable. Python identifies that statically. There's another important rule. Python identifies the scoping of a variable, and that scoping cannot change within a particular context. In other words, it is not possible for a function to have x referred to as a global variable here, and then x referred to as a local variable. It cannot change. In the body of a function, the scoping of x must always be local, or always dereferenced, or always global. And that starts to give us a little bit of insight into what was going on before. When we have some code like this, Python can see x equals, I know this is a local variable. It's going to shadow whatever this x variable is here. This is just a reassignment of x. What Python cannot see is it cannot see the right-hand side of this expression, because the right-hand side of this expression could be absolutely arbitrarily complex. It could require runtime data. It might make use of something like eval. If I did an eval input, something like this, Python can't understand what's going on there. It could be any code that could be evaluated, anything that could be run here. It depends on what the runtime input looks like. And so as a consequence, all Python can do is look at those static forms. Note, one thing Python cannot do is look through something like this, where you assign x into the locals. Python can't see this because here, this portion could be arbitrarily complex. It could require some sort of runtime state or runtime knowledge, so Python cannot statically identify this. And so, in an example like this, Python will guess that there is no hacks x to x. In fact, if I put x here, it'll assume x is global, because it cannot see through this. It can only see those static forms, and it cannot see the right-hand side of an equal sign. It can only see the left-hand side of an equal sign. Which means when Python sees x plus equals 1, Python says, well, that's the same thing as x equals x plus 1. And the left-hand side of this says, oh, it's a local variable. Except in this case, our intention was that x was a global variable, because you can see it's not being passed in and it's being referred to before it's being assigned. Well, what Python's doing here is it's saying x equals must be a local variable, generate the bytecode for a load fast, and then when it goes to execute this code, it tries to load that variable, cannot find it because it doesn't exist in the local scope, and it gives you that unbound local error. Python's parser is guessing wrong. Python sees x equals x plus 1, matches it up to a pattern that creates a local variable, and says this must be a local variable. But your underlying intention was that it was a global variable. It's just that Python didn't have that information. This is what the global and the non-local keyword do. They don't add new bytecodes. They don't do anything mechanical. They just hint to the parser. You're going to guess. You're going to guess wrong because you're going to see a form that you think you recognize as creating a local variable, but it doesn't. And I'm going to warn you ahead of time that for the entirety of this scope, this thing is actually global. Please generate the correct bytecode. And you can see all this does is it hints to the parser how to generate the correct bytecode to actually make this a load global. And that's all that it takes to make this correct. Now, x and every place it's referred to is a global variable. This does not create a variable. This is not a variable definition. It doesn't allocate space for this. All it does is it hints at the parser. And it's the same thing with that non-local keyword. Here, Python sees x equals x plus 1. Because Python sees x equals x plus 1, it's going to say, well, x equals, I'm going to stop there. I can't see into the right-hand side of this expression. And so I'm going to assume that this must be a local variable. But it's not a local variable. It's in this closed over scope. So we just have to tell the parser, make this a load deref, please. This is actually a dereferenced closure variable. And Python guesses correctly. And this code will work correctly. If it's the case that Python wouldn't make a mistake here, for example, if I did x plus 1 equals y, here Python sees y equals, okay, we're going to create a new local variable called y, and x plus 1, well, where does that x come from? Well, I can't see an x equals anywhere here. I can't see anything that creates x. So it must be this closed over variable. Well, here, this is absolutely fine. We can load from a closure variable and store to a local variable. That's completely fine. We just can't have a variable B or a name be both local and dereference, or local and global within the same scope. It has to be one or the other for the entirety of that scope. And here, there's no guessing wrong. And so there's no need to add a non-local or a global keyword at all. Now, one thing that I want to draw your attention to that also explains what's going on is, bear in mind, in the previous example, there is a material difference between the behavior if X is a mutable or immutable type. If X is immutable, we cannot change it in place. That's what immutable means. So if we want to do something like add one to an integer or uppercase a string, what we can do is we can say, perform that operation, give me a brand new piece of data, and make X refer to that brand new piece of data and then garbage collect the old piece of data. In other words, if I look at the IDs of X before and after an operation like incrementation, I'll see the IDs change because the new X is not changing the old one in place. It's actually allocating some new memory and giving you a new value subject to the operation of incrementing. This is the case irrespective of how we write this, whether we write this in X plus equals 1 format or X equals X plus 1. No matter what, those integers are immutable. And it's the same thing with variables like strings. If we had X equals ABC and we did an X dot upper, X equals X dot upper. Well, here it's very clear. This performs an operation that gives you a copy, and then it just says, okay, now X refers to the uppercase ABC, and the old data can get deallocated if there's no other references. However, in the case of the list, because the list can be changed in place, because it is mutable, this does not require an assignment. It's just going to that existing data and changing it where it stands. We don't have to do a rebinding of the name. So the name is still referring to the same data. You can see the ID doesn't change. And this is why the examples with the list appeared to have the ability to affect something outside of the scope. What we're doing is we're passing around a name that refers to some object. And as long as we have the name that refers to that object, we can go to that object and mutate it in place, as long as that object happens to be mutable. Therefore, in the different scenarios that we had, if X's was a mutable piece of data and we pass it in, note, this is not performing a rebind. This isn't saying X equals anything. This is just saying go to the actual X's, whatever it was, and go and mutate it in place. And what we would see here is after this function is called, we would see that it went and it updated the actual X's data, whatever this piece of data, wherever it was located, however it came into being. If this happens to be a string, since we can't do this, or if this happens to be an integer, since we can't do this, well, here, the only thing we could do is we could say, okay, create a new binding within this scope that's the original data, modified in some way, not necessarily modifying it in place, but applying some operation or some computation to it. And that's the other piece. When we think about scoping in Python, we should think about what the parser can see, what Python can statically analyze, and we should think about mutability and immutability. Those two pieces give us full understanding of why all of the previous examples worked the way they do. In the closure example, it's the exact same case as before. Here, if we do an excess.append, no big deal because we're referring to this data directly. We're not rebinding that name. So if we were to rewind all the way to the beginning puzzlers that we had, we can see every one of them makes a lot of sense why it is the way it is. Let me show you what I mean. If we look at the first example, here we have an immutable piece of data in the global scope. We pass in the name for this immutable data. This says, you know what, that's immutable data, so I can't change it in place. So this is saying X equals X plus 1, create a new name binding with some new distinct data, and you can see where the IDs are different in the after here than in the before when you're inside the function, and you can see the underlying data didn't change. Well, of course, it's immutable. It can't change. The scoping of this was limited to this function because inside this function, we actually created a brand new piece of data that just happened to have the same name, but that binding is limited to this scope here. If we take a look at our next example, if this was solely a global variable and In this example, we said x equals, or x plus equals 1. Here, Python was seeing x equals x plus 1, saying, oh, x equals must be a local variable, trying to then execute this. And when it executes it, it's actually executing the right-hand side first and saying, well, hold on a second. Where did x come from? I thought this was a local variable. It doesn't exist yet. And giving you that unbound local error. It's exactly why this happened, because a parser is guessing wrong. If we look at our next example, all we have to do is tell the parser, you know what, guess right. Even though you see x equals, this is actually intended to be rebinding in the global scope. It's intending to be taking whatever that binding was at the global scope and just replacing it. This is always a global variable, and this works as expected. If we take a look at our next example, where we return, well, we do this all the time. There's nothing too fancy here. You can see the ID has changed because the x that is being returned from this function is a brand new piece of data. It is, after all, immutable data. Strings, integers, all the other numeric types, all the other textual types, the tuple, the frozen set, these are our core pieces of immutable data, which will all show the same general behavior. Now, if x is a list, note, this is passing the name of x in. This is not performing a rebinding. It's going to the original data and mutating it in place. Because it's mutating in place, we should see the effect of this operation on the outside because it changed the one piece of data at this one particular memory address. You can see it's the same data that's being used everywhere. This is why those examples worked the way they did, and why those examples did not need a global keyword at all. In fact, irrespective of whether I pass in or refer to in the global scope, here there is no possible confusion because there's nothing that's creating a binding. And so there's no need and no effect from adding global or whatnot. Now, if I add something like non-local here, of course, this is going to be completely nonsensical. It's going to say this is impossible. So there really isn't anything that's added. The most I can possibly do is tell it to do something completely nonsensical, like this is non-local even though there's no closure. And keep going. I mean, you can see this global keyword doesn't really need to do anything. It doesn't need to exist in the case of this being mutable data because we're not confusing the parser. Here, in this example, very similarly, if we return some data, well, we do that all the time. That's no big deal. In the case of the closure, just like in the case of that global, we're getting an unbound local error because Python sees x equals x plus 1 with the immutable data, and it just doesn't like that. So it says, I can't figure out where this x came from. You told me it was a local variable by saying x equals, and you get an unbound local error. And if you add that non-local keyword, the behavior is very similar to what we would do in the global case. We're just giving a hint to the parser that this variable is in the closure. One thing to note here is that in the inside case, we can see that this x plus equals 1, again, it's immutable data, so it will create a brand new object. We cannot change it in place, and that's the core to our thinking here. And then finally, in the case with the list in the closure, you can see we didn't really have to do anything too fancy because we didn't create any space for confusion for the parser. We just refer to some data by some name, and we can pass those names around as deeply as we want, and they all refer to the same underlying data. We're not shadowing, we're not replacing this binding. And thus, this doesn't need a non-local keyword. It works exactly as you might expect from the previous examples. Prior to the introduction of the non-local keyword in Python, well, we still had this problem of having closures and having to refer to them. And one of the tricks that we would do is we'd make use of the Python parser's visibility into, or the assumptions the Python parser would make. What we would do is we'd create a cell, we'd create a value, a mutable thing like a dictionary or a list with one entry, and we do some syntax like this. And note, this syntax here doesn't say rebind cell. It just says go and find whatever that data that I refer to as cell is, and go to its 0th element and change that. And so this does not mislead the parser. Here, the parser can very clearly see this is a dereferenced closure variable, even though I don't need that non-local keyword. And this is more or less how we do this in the era before the non-local keyword. We would just make use of the parser not getting confused when you do something like a set attribute or a set attribute or a set item operation like here. Now, if you're curious about what this closure is, you can actually see what's going on there. If you take a look at the underscore closure, you can actually see this looks very, very similar to the previous approach. historically, when we wanted to get around this problem, we didn't have that non-local keyword, we'd create our own code level, user level cell, and we'd manipulate that. Well, these days we don't have to do that anymore because we have that non-local keyword that points us in the right direction, but the underlying mechanism is more or less identical. There is this underscore underscore closure that is just a tuple containing each one of the cells with some cell content. You can see there's this indirection that allows us to pass everything by name, refer to it, identify exactly what we want to change, and change it in place. This closure is mutable data. And so our conclusion is as follows. Python scoping is determined statically. The Python parser only does a couple of things that are interesting. It, for example, does name-mangling. It does things like sets you up for the zero-argument super, and it determines where variables come from by saying, if I see one of my local patterns, it's local. If I see one of those local patterns in a scope above me, in a function that's creating me, then it must be deref, it must be non-local. And if I don't see it there, well, it must be global. And of course, again, there is one other possible location, the load name, where it searches through a couple of different places, but that's generally pretty difficult to generate these days. It used to be a lot easier to generate that. The non-local and the global keywords are only necessary to inform the parser when you suspect the parser is going to get something wrong. If you keep in mind the forms that create names in scopes, which are pretty obvious, x equals is one of the most common ones, and you just keep an eye on that, then it should be pretty obvious when you're saying x equals to create a local variable and the parser will get confused. And in those cases, you need the non-local or the global keyword. It doesn't hurt to add it. Maybe it makes it a little bit noisier. It adds a little bit more stuff to your function, but it doesn't hurt to add it if the parser is already going to guess right. But all these keywords do is a hint at the parser. It is important to note as well that the non-local and the global keyword apply to the entire scope that you're working at. A Python variable can only be local, deref, or global, but it cannot mix. It can't go from being global to local within the same scope. It has to be entirely one or the other within a given scope. And so that non-local and global keyword can't then trigger some behavior later on. You basically have to put it at the very top and say, look, ever after, this is what this is going to be, because it can only be that in that scope. Finally, when you think about the calling convention in Python, think in terms of call by name and think in terms of mutability and immutability. When you think about things like pass by value and pass by reference, you're thinking about where copies are being made or if copies are not being made. Python's pass by name is actually pretty close to pass by reference because under the covers, everything is really just passing a reference to a Py object pointer. But in general, the way we describe how Python's calling convention works is pass by name. What you're doing when you're calling a function is you're passing a name that refers to some data. If it refers to immutable data, well, you can look at that immutable data, but you can't change it. That's what immutable means. If it refers to some mutable data, you can look at that data and you can change it in place. That's what mutable means. What you're passing around is a name referring to that underlying data, which means if you call a Python function with an int, you're not making a copy of that int. It's not passed by value. You're actually referring to the original int. It's just that because these pieces of data are guaranteed to be immutable by the interpreter, they cannot be changed. Take into account how the parser works. Take into account mutability and immutability, how things like identity and equality work in Python. And all of these answers will be very clear and very obvious to you the next time you run into an unbound local error, the next time you have to say, I think we need a non-local keyword here.